I'm going to start anyway because we have a lot of stuff to go over today. I hope we're going to finish it in time. If not, then I'm going to start skipping some stuff at some point. So yesterday, we talked about probabilistic modeling, Bayesian probabilistic modeling of functions, and analytic inference of the W in the last layer. We found the mean for that W in the last layer. Today, we're going to go over all of these topics. We're going to go over uncertainty over functions, scaling up these ideas, scaling up even more using stochastic approximate inference, uncertainty in shallow models, stochastic approximate inference, inference in very large models, and real world applications. And let's see how much of that we actually managed to finish. Come again? You can't hear. Okay. Is that, okay. I'm just going to walk like that, maybe. Yeah, okay, so a lot of stuff, basically. As a reminder, all of these things are going to be actually already are on the website, and you can use the slides to follow up or to go over the derivations a bit more slowly. Yeah, so we're going to start with talking about uncertainty over functions. And just as a quick reminder, this is a model we had yesterday. I wrote the model slightly differently. So I wrote it in a way that makes it a bit easier to extend it for the stuff we're going to do today. So we have the prior distribution, which is P of W for some W K by D matrix. K is the number of units in the feature vector. D is the number of output dimensions. Each W element KD follows a normal 0 S squared distribution, which is the same as saying that we had a normal distribution over the entire W vector from last time, or the entire matrix, where we had S times S squared times identity matrix last time. The likelihood, P of Y, for all data points Y, condition X, and some W, is the product over all data points of a normal distribution for each yn with mean fw of xn and some variance sigma squared, where fw of x is just w transpose phi. Phi was the k-dimensional feature vector that we had yesterday. We found the posterior, so we spent quite some time finding the posterior for this simple model. We found that it was a normal distribution with this mean and sigma that we have over here, and we found the predictive mean. We found the mean of the predictive distribution, which is P of Y star, condition X star for some new test point X star, and conditioning on the data as well, on the X and Y pairs that you gave me. We found the mean. I think I asked you as homework to find the variance, which is this predictive variance that we have over here, sigma squared plus phi on X star transposed sigma dash times phi. So this is actually quite interesting. We have two components in the uncertainty over here. We have sigma squared that comes from the likelihood, and we have that other term that comes from the posterior distribution. First term, okay, yeah. So the first term over here comes from the likelihood. So we had over here P of Y condition X and W followed some product of normal distributions, and each one of them had a sigma squared. And that's the same sigma squared that we have over here. The second term comes from the posterior distribution, which is that sigma, capital sigma prime that we have in the predictive variance. And these two terms actually capture different properties of the uncertainty, different types of uncertainty. The first one captures what we call aleatoric uncertainty, or amount of observation noise that we have. You can see that in the left-hand side of the figure, where we have very noisy data, in which case we're going to have very large sigma if we try to optimize the sigma, for example, to maximum likelihood with the sigma. On the right-hand side, on the other hand, we have a large amount of epistemic uncertainty. It's the uncertainty that comes from the posterior. So that's the right-hand side is it will be large when, sorry, the right-hand side corresponds to the second term in that predictive uncertainty. That term, that uncertainty will actually decrease if you give me a label. So if you give me the label y star for that x star, and I update my posterior, and I update my predictive distribution, and I update my predictive uncertainty, uncertainty over here will decrease and become smaller, because now I know what the value over here is. And the uncertainty will decrease only from the second term in the predictive uncertainty, only from that phi transpose sigma dash phi. So the first term again is called aleatoric uncertainty. It comes from the corrupting noise that we had. It comes from the word aleator in Latin, or dice blur. Basically, if you roll a pair of dice again and again and again, you're not going to decrease your uncertainty in your observation. And that's the same as observation noise that we had in the likelihood over here. So if you follow the generative story, and you find, basically you give me some W, and I generate some data, condition the W using the likelihood, then every time I'm going to add noise with sigma squared. And if I generate an infinite amount of data, it's always going to have some inherent ambiguity, which is due to that sigma squared term over here. That's basically that's the essence of this type of uncertainty. You can find this sigma if you just do maximum likelihood over the sigma itself to maximize the probability, marginal probability that we talked about last time, marginal likelihood of the sigma. You can also assume that we know that in advance, which we're going to see later. Second term that we had over here is also the same as the uncertainty over the function values themselves before adding the corrupting noise. So if we define f star to be a random variable, which is going to be W transpose times phi of x star, where W is a random variable that is the stochastic matrix that we had. Then the variance of f star is going to be this term specifically. And you can actually show, I didn't bother doing that over here, it would have taken too much time. You can actually show that the uncertainty, predictive uncertainty, can be decomposed as a predictive uncertainty over f star and the uncertainty given f star. And that again will be high for far away data, even in the noiseless case, even if you give me a likelihood sigma to be 0 exactly. And it will diminish near the data, or if you give me a label for the x star. And that comes from the ancient Greek episteme, or knowledge, understanding, knowledge uncertainty. Let's say that we want to evaluate our predictive uncertainty for a very large feature vector, which is a bit difficult if k is very large because we need to invert a k by k matrix. This is a good excuse to introduce approximate inference, which will simplify some of our derivations, some of our computations, also some of the derivations. And later on we'll see why it is actually much more interesting than what we're just doing here now. So in approximate inference, we approximate the posterior. So we had P of W condition X and Y. And instead of finding the posterior itself, which is often computationally expensive or intractable and so on, we're going to define a simple distribution, Q, of W, over the same event space, with the same outcomes that W would have taken. But Q has some parameters theta. Q is also called the variational distribution, and the theta is also called the variational parameters. This technique is also called variational inference, and I'm going to use all of these terms interchangeably throughout the talk. For example, Q could be a Gaussian distribution where theta would be the mean and the sigma for that Gaussian distribution, the mean and covariance for that Gaussian. We often omit theta as a side note to avoid clutter, and just going to write Q of W or just even Q, and often swap theta for mu and sigma. So let's look at an example. I have a posterior which is normal 0, 1, and I give you two approximating distributions, Q1, which is normal 1, 1, and Q2, which is normal 10, 1. Which one would you choose? Which one do you think is a better approximation? Like, let's say, show of hands, who thinks that Q1 is a better approximation? Who thinks that Q2 is a better approximation? Okay, so this was an easy example. What do you think now? Q1 is normal 0, 2. Q2 is normal 0, 10. Which one do you think is a better approximation? Who thinks Q1 is a better approximation? Who thinks Q2 is a better approximation? What about now? We have Q1 is normal 10, 1, and Q2 is normal 0, 10. Which one would be a better approximation? I think it's becoming much more difficult to decide intuitively. The one that would give us better predictions, that actually would fail because that would just lead you to the same maximum likelihood failure we had last time. Like we're just going to use a mean for the approximating distribution to be the maximum likelihood estimator and zero uncertainty. We actually need some measure of how similar these distributions are to the posterior distribution. So we're going to choose a measure of similarity, quote unquote. It's very much not a similarity between distributions. It's going to be d tilde, which is not necessarily a distance. It doesn't have to be symmetric. Then we're going to minimize whatever measure we commit to. Basically that means that if d of Q1 from posterior is smaller than d of Q2 to posterior, then the core principle of VI says that Q1 should be chosen over Q2. Basically, you saying that according to the measure that I chose, the measure of distance of similarity between distributions that I chose, that tells me that Q1 must be better than Q2. There's lots of other issues. We can come back to that later if you want. Okay, so we start from that axiom of like, if d tilde of Q1 is smaller than d tilde of Q2, then Q1 should be chosen over Q2. What if we have two divergences, D1 and D2? One saying to select Q1 and one saying to select Q2. That actually leads to a very interesting observation that unlike in full Bayesian inference, when there's only one way of doing things correctly, in approximate inference, we're basically shifting from a dogmatic view into a much more pragmatic view of Bayesian inference, of Bayesian probability theory. We often actually end up choosing the D that is mathematically convenient, that we can actually use to do tractable approximate inference. For example, the Kullback-Leibler divergence. It's a very nice, it has very, very interesting properties. It's basically the integral over Q of the log Q over P, integrating with respect to the stuff that goes inside the Q. Let's try to get an idea for some of the properties for this distribution. If we have a k-dimensional discrete probability vector, well, two of them, Q and P, then the Kullback-Leibler is just going to be the sum of the probability masses, Qk, times log Qk over Pk. When the two distributions are the same, the Kullback-Leibler will be exactly zero. When the two distributions are different, the divergence will be positive. Kullback-Leibler is not symmetric, and if one of these QKs is zero, it is actually ignored in the KL. It's the same as like dropping that from the sum. Whenever QK is larger than zero, it must be that PK is larger than zero as well for the KL to be finite. And as some homework, you can find examples for all of these properties. For example, the pair over here of two three-dimensional probability vectors would give you one of these things, symmetry example, symmetry property. So what if we want to approximate continuous variables like W that we have? Kullback-Leibler for Gaussian distributions, Q normal mu naught S naught squared, P normal mu1 S1 squared, actually has a very nice form. It is given by this equation, which I'm not going to read. Kullback-Leibler has also a very nice property that if x1 and x2 are independent under both P and Q, then the Kullback-Leibler of the joint is the sum of the margin of the Kullback-Leiblers of the marginals. So it's just this equation again, which I'm not going to read. So that basically means that if you give me a multivariate Gaussian distribution of k dimensions, I'm going to write x equals x1 to xk, and we have two of these normal distributions in over the k-dimensional vectors. Then from the independence of x1, x2 up to xk on each other, the Kullback library would just be the sum of the individual KL terms. So that's a very nice form. This is like a very useful slide, so you can just go back to that later on if you want to use that as a reference. We want to find the posterior. We want to approximate the posterior P of W condition x and y using some q theta. So we want to minimize the KL of q to the posterior by changing theta. We want to wiggle theta in order to get the KL to be smaller and smaller. Remember the definition for the KL over here. Let's basically start expanding stuff. So we have the KL between q and the posterior, which is by definition just the integral of q log q over p, or q log q over posterior. And remember by Bayes' law, the posterior is just the likelihood times the prior, divided by the marginal likelihood, which can just rearrange some stuff, and then just write it down as a sum, pulling out some of the product terms. So we have integral of q of basically what is negative log likelihood, plus the integral of over q of log q over p, which is the Kullback library between q and the prior distribution, plus another integral over q of something that doesn't depend on q. So we can pull that out of the integral. And what we get is just the negative expected log likelihood plus the KL to the prior distribution plus the log model evidence or log marginal likelihood, log P of y condition on x. Everyone is happy with that? This is a core equation that we're going to start building on. Yeah? What I'm going to do next, I'm going to take the last two terms over here and move them to the other side of the equality. What I'm going to get is and I'm going to move the KL to the other side as well. So I'm going to swap these two terms at the bottom with a term at the top. What I'm going to get is that the expected log likelihood minus the KL to the prior distribution, which is what we call the elbow or the evidence lower bound, you're going to see soon why, equals the log evidence, log marginal likelihood, minus the Kullback library, the KL between Q and the posterior distribution. Yeah, everyone is happy with that? Yeah? Now, the term that I have underlined in this last line over here is always positive by one of the properties we talked about, properties of the Kullback library. Therefore, what we have is that we have something on the left-hand side equals the log evidence minus a positive thing. So what we can do, we can remove that positive thing and get a lower bound. So now the thing on the left-hand side is lower bounding the log evidence. And I have a pretty picture over here that basically shows that the left-hand side was equal right-hand side minus that positive term. If we remove that positive term, the left-hand side now is smaller equal to the right-hand side. Everyone is happy with that? Yeah? You can come back to the derivation later. The main key results from this derivation is that if we want to approximate the posterior using some Q, then we want to minimize the Kullback library between Q and the posterior, which is the same as maximizing a lower bound on the model evidence. We have the integral of Q, log of the likelihood, minus the KL between Q and the pi distribution, and this is called the elbow. So minimizing the K result to remember from here is that minimizing the KL to the posterior is equivalent mathematically exactly the same as maximizing the elbow, the evidence lower bound, which is the equation over here. Now this equation is actually very, very, very interesting. It has some very interesting properties. What does it mean to maximize this elbow? The first term in this equation basically tells us how well can we explain the data. It basically, if possible, Q would put all of its mass on the maximum likelihood estimator, on the MLE itself. It will basically just say, I'm going to take the best prediction that I think it is, that is going to lead to lots of other failures with sigma equals 0, and that's what I want to do. However, the second term over here penalizes us and tells us how close we are to the pi distribution. So we would get simplest Q. Basically it tells us that we want to get the simplest Q. Under our definition of simplicity, the pi defines what is simple, that can still explain the data well. If we only optimize the second term, Q will just collapse to the pi, will just become the pi itself. That will be the optimum for that elbow. Okay, so we have this key equation, which is the evidence lower bound. Which terms can we actually compute? So if you have a Gaussian pi distribution and a Gaussian approximating distribution Q, then we can compute the second term over here analytically. That's what the equation that we had in the first few slides. For a Gaussian likelihood, we can also compute this first term analytically, because it's just going to be the log of a Gaussian, it's just going to be a quadratic. Then integrating that with respect to a Gaussian, you can try that at home. Much more complicated likelihoods, though, would make this quite challenging. For example, if you want to do classification, you can't just use the stuff that we have over here. For that, we need to introduce new tools. We need to talk about stochastic approximate inference. So let's try to do a classification task. Let's try to get uncertainty in classification. We want the notion of epistemic uncertainty in classification. Over here we have a nice example of two possible functions that could explain your data, which is like, imagine the diabetes diagnostics that we had at the beginning. And P is the probability that you have diabetes, and this is 0 image over here. You have some training data over here that says no diabetes, data over here that says yes diabetes. And we want to get an idea of over here we have high uncertainty. The generative story in this case would be nature chose some probability function, P of x, that maps from RQ, number of input dimensions, to 0, 1 to the power of C, like C probability over C classes, probability vectors in the simplex of C dimensions. P is a probability vector as a function of x. For example, P could be this simple softmax function that we're going to talk about a lot later. You can see the form for how the softmax function is defined. For n patients, 1 to n, or data points, or inputs, you're going to generate n labels by sampling from a categorical distribution that has probability given by P of x. And we're going to encode each one of these yns as one-hot vectors, for example, 0, 0, 1, 0, 4 classes corresponds to class 2. So this is a bit of a complex slide. Our model is defined as following. We have a likelihood. Let's start from the likelihood. Likelihood is just, we're going to model our, we have some data. We have some examples of inputs and output labels. We believe that it was generated from some categorical distribution that had some probability vector as a function, as an input to that categorical distribution. So we want to model that function. We're going to model the probability function using some Pw of x, where W is a k by c matrix. Similar to before, we assume that we had a fixed feature matrix, feature vector. The likelihood is defined as element C in this following probability vector. So for each C, I'm going to take WC to be some k by 1 vector, because W is the k by c matrix. We're going to write W just to be the collection of all of these columns. It's going to be, well, all these rows, it's going to be a K by C matrix. We're going to define what we call logits, which is W1 transposed phi up to WC transposed phi with phi the feature vectors we had before. That's going to be FW. We're going to define our probability function, PW, to be the softmax of F of W. Softmax that we defined before, some squashing function. We're going to define our likelihood to be, take that element C in that probability vector, and that's going to be the probability that we think that we take a class C. The probability for the entire data set is going to be the product of each one of these individual likelihood terms, which is going to be the same as the product of Y transpose P. P is now the entire vector, and Y transpose is the one hot encoding that we had before. Y, if we have a one hot encoding transposed P, that's the same as selecting the C element in that vector and then just multiplying them together. So it's just convenient using vector form for a lot of these things. We're going to define our pair over W to be vectorized W, so it's going to be just a long list of numbers. We're going to still write W instead of vec W for simplicity. We're going to put the same pair distribution as before. We're going to be normal 0 S squared. Any questions about this slide? Yeah? Everyone is happy with how classification is defined. Okay, I'm going to ask a question. Who thinks that they can explain what's going on with this slide? Okay, good. Who thinks that they understand the likelihood of this slide? Okay. Now this is actually very interesting. So just like I actually am trying to just communicate the intuition over here, but that makes the formalism a bit difficult. So who thinks that we understand the generative story? Okay. Let's go over that in a bit more detail. I think we have enough time. If we don't, we're going to skip some of the later stuff. So remember generative stories from last time, from yesterday. The generative story is basically the way that we believe our assumptions about how the data was generated. Over here, my assumption about how the data was generated is that there exists some function, P of x, which is a function that takes some, let's say, patients, like images of your blood vessels in the eye, that example that we saw yesterday, and spits out probabilities, the probability that you have diabetes, for example. And that's some natural phenomenon, that's some function that we don't know what it is, but what we do know, we observe some realizations from the actual yes-no answers, do you have diabetes or not, from these different images of blood vessels in the eye. So in the example over here, the function would just be a very silly function, which is just looks like this. Happens to also be the softmax function, that's really not important. The main point just looks like that. And if a patient happens to be in this part of the X space, then the probability is going to be very high. I'm going to sample from categorical distribution. A high probability I'm going to get 1, you have diabetes. If the patient happens to be in this part of the space, I'm going to have a very small p, near 0. I'm going to sample from categorical distribution, and I'm very likely to have basically y equals 0. You don't have diabetes. So that's basically how I believe, that's my assumption about how the data was generated. Yeah? Softmax is just a function that has this nice form over here, and which we'll actually use later on, but I just give this equation over here because it's nice. This is not important. This is actually, I think, the more important stuff. So we know our assumptions about how the data got generated. So how can we encode these assumptions into a probabilistic model? Well, we know that the data was generated from some categorical distribution that was operating over some mechanism, some function P of x that mapped some images of your blood vessels in the eye to the probability that you actually have diabetes, yes or no. So we're going to try to build a model of that process. In this case, the model is very simple. It's just going to be take any feature transformation, phi, which is what we talked about yesterday, assumption that we have that someone gives us phi in advance, which later on we're going to remove that assumption. And what I'm going to do with that phi, I'm just going to multiply that by some w, which is a k by c matrix. Meaning that instead of having a k-dimensional thing, I'm now going to have a c-dimensional thing, which is this fw. Fw is a c-dimensional thing. Taking that fw and plugging that into a softmax function, which is the function that we had defined over here. So this is the softmax function that takes fw of x1 up to fw of xc, basically gives us back a probability vector, squashes all of these values to be between 0 and 1. And then my assumption is that I just took those probabilities and used these in my generative story to generate whether I have cancer or not, whether I have diabetes or not. That basically means that the probability that I believe that I have class 1, yes, diabetes, would just be the element number 1 in this probability vector, which is going to be that one. The probability that I believe that I have no diabetes will be element number 0 in this probability vector, which is this one. Which basically means that if my w times phi was very large, then the probability that I believe I have diabetes would be here. Probability that I believe I have no diabetes will be here. That's the input now to that softmax function. Go over these slides later. Try to make sure that you understand these things well. I'm going to continue, and if there's any other stuff that actually relies on these things, then I'm going to highlight that. So we define some pi distribution over this w. And we want to do inference. We want to do, well, actually what we care about doing at the end of the day is doing predictions. What I want to do is I want to find the probabilities for some y star, condition x star, and some data. I want to find the probability that I have diabetes, conditioned on my own image of the blood vessels in my eye, and some data that I gave you through some other patients. Again, by the laws of probability theory, it's just going to be the integral over that. For that, we need the posterior distribution. The issue is that the product of the likelihood, which is what we had over here. So over here, remember, P is just the softmax of F. So this is just Y transpose softmax. So this is Y transpose softmax. So that's the same. That's basically the likelihood that we defined before. That's not conjugate to a Gaussian distribution. Or in other words, that is not something that we can do easily. Can't integrate or sum that explicitly. So for that, we're going to use an approximate posterior. We're going to define So we're going to do an approximate inference technique. We're going to define an approximate posterior. For approximate inference, we need the log of the likelihood, which is what we had in the elbow equations from before that you were happy with. The log of the likelihood for this softmax distribution, for the softmax likelihood. Again, so this is the softmax likelihood. The log of the likelihood is just going to be F, which is the W transposed phi at position C, minus log of sum of exponents of F. With F1 up to Fc is just being W1 transposed phi up to WC transposed phi. The expected log likelihood is this equation over here, which is very nasty. We have a sum of data points of the integral of this thing over here with respect to some Gaussian distribution, where this thing over here is W transpose phi. We can't integrate that either, very annoyingly, because of this log some exp over here. We need new tools. So we're going to take a small, very quick break. We're going to talk about Monte Carlo integration. And we're going to come back after that to the classification example. So this is a very useful tool for whatever you end up doing. So it's probably worth listening even if you tuned out for the previous slide. Now define some px to be any distribution which is easy to sample from. We're going to define fx to be some function of x. Assume that it is difficult to evaluate the expectation of f with respect to p. So we can just do a normal Monte Carlo integration. We're going to sample x1 up to xt from p. We're going to estimate e hat, just going to be 1 over t samples of the sum of f at position xt. This estimator e hat is unbiased in the sense that the expectation of e hat with respect to p equals e. You can show that at home. But that's actually not what we need. That's actually not what we want over here. Remember that we need to optimize that elbow, that very long, nasty equation that we had before. Meaning that we actually need to find the derivatives. We need to find the gradient for that equation with respect to the stuff inside the distribution. So we basically need an estimator of the derivative of the integral. So let's define g of theta to be the gradient of L of theta. L of theta is going to be some function that depends on theta. We're going to interchangeably use g, which is the gradient of L, or L prime, which is the derivative of L with respect to theta, or the derivative of L with respect to w theta, which is the derivative of L with respect to w theta, where w is some random variable that depends on theta. Could be what we had before, the Gaussian, could be something else, could be anything. If we had an unbiased estimator of g, then we could do stochastic, we can use any stochastic iterative method to optimize L by just plugging that g hat into any stochastic optimizer like Adam or SGD or whatever it is. If you actually follow theta n plus 1 is just theta n plus small step of g hat, then that is the direction of steepest ascent on average. And we actually know that we will converge under some mild assumptions to the correct optimum for L. Let's look at a very simple example. We have this very simple L, which depends on mu and sigma as two parameters. And that is just going to be the integral of w plus w squared, where w just follows a normal distribution, so we integrate that with respect to a normal distribution. We can actually do that analytically. So we can evaluate that as L just equals mu plus sigma squared plus mu squared. So we can differentiate that with respect to mu analytically as well. That's just going to be 1 plus 2 mu, which is just going to write that as g mu, or like delta L over delta mu. But if we do Monte Carlo integration, we're actually going to get very weird results. So let's do Monte Carlo integration for L. We're going to get w hat squared plus w hat plus w hat squared with some numbers, w hat sampled from normal distribution with mean mu and variance sigma squared. So the derivative of g with respect to mu, the derivative of g hat, well, the derivative of L hat with respect to mu would be 0, which is very weird because obviously it should not be 0, because obviously L hat depends on mu. For example, as you increase mu, you also increase L, and therefore you also increase L hat. So this is very much incorrect. So what's going on over here? Well, it turns out that L hat actually depends on mu for w hat. And w hat is actually a function of mu as well as some random variable epsilon hat, which is independent on theta, independent of theta, of mu, and so on. So we can actually write w hat as a realization. You can write it down as w hat equals some function of theta and epsilon, which is, for example, mu plus sigma times epsilon, where sigma hat, so where epsilon hat follows a normal 0, 1 distribution, which doesn't depend on mu, doesn't depend on sigma. So we can basically rewrite L hat as mu plus sigma epsilon hat plus mu plus sigma epsilon hat squared, which is going to be a bunch of terms, and the expectation of that, well, and the derivative of this bunch of terms with respect to mu is going to be 1 plus 2 mu plus 2 sigma epsilon hat, and the expectation of that with respect to epsilon would actually be g. So that is actually an unbiased estimate of g. So this technique is also called the reparametrization trick, also known as pathwise derivative estimator, also known as infinitesimal perturbation analysis, also known as stochastic backpropagation. In general, for any function fw in distribution Q, we want to estimate the gradient of L, so w can be, if w can be reparametrized with a differentiable g, such that w equals g of some parameters theta and some epsilon that is not dependent on theta, then g hat, then the derivative, stochastic estimator for the derivative of L will just be the derivative of f at g times the derivative of g with respect to theta. And then just plug that into the stochastic estimator. For Gaussian G, or Gaussian Q, W is just G of mu sigma and some epsilon, so that's just going to be mu plus sigma epsilon. Derivative of G is just going to be 1 with respect to mu, or epsilon with respect to sigma. So G hat is just going to be the derivative of f times 1, and derivative of f times epsilon when you look at the derivative with respect to mu and sigma. And you can actually even plug back w over here, and you're going to get that the derivative of g with respect to w, with respect to mu, is just going to be f prime at w. Derivative of g of L with respect to sigma is going to be f prime at w times w minus mu over sigma. I'm going to go back to our simple equation, simple slide from before, which had this very, very long equation, which if you didn't understand where you got it from, you can go over the slides later. We're going to do the same technique that we just learned over here. So we're going to use Monte Carlo integration. We're going to sample some epsilon from normal 0, 1. We're going to write vectorized w as just mu plus sigma to the half times epsilon. Reshape that vectorized w back into some w hat. We're going to rewrite, instead of taking fw that we had before, we're going to write that as f theta and epsilon hat, which basically gives us a stochastic estimator for this L, which is just going to be sum of f theta epsilon hat minus log some exponent of f epsilon theta epsilon hat. That's all. And we know that the expectation of that thing, respect to epsilon, will be the thing that we actually care about. And the expectation of the derivative of that, respect to epsilon, will be the derivative of the thing that we actually care about. So that allows us to optimize. That allows us to optimize the elbow that we talked about before. Okay, after that very, very long list of things which are very difficult to understand, let's look at some pictures. So we start by just sampling, initializing some theta at random. We have some random neural network that we don't bother optimizing yet, so we just have some randomized theta. We sample some epsilon 1, we get some function. Sample some other epsilon 2, we get another function. When we optimize the elbow with respect to theta using the tools we talked about, we're going to get that in sample epsilon 1, we're going to get some function that at least goes near the data on the axis where you have data. Another function that again has the same property, goes near the data when you have data. Far away from the data, it can have very different values. Near the data over here, you can see all of the function values take the same, all the functions take the same value. Okay, so it's enough mathematics for a few slides. Let's talk about some uncertainty again. Let's talk about some conceptual stuff. How do we get epistemic uncertainty in classification? How do we know when your image of your blood vessels in the eye is far away from the training data? That's actually quite different from the regression case. But at least we finally have the tools to be able to talk about that in a formal language. So we're going to use tools, we're going to use various measures of uncertainty from the field of information theory. Basically, we're going to talk about each one of these capturing different desiderata, different properties of uncertainty. We're going to talk about entropy, which is just the sum of possible outcomes where you multiply the probability of that outcome with a log probability. So for example, if you have P of X is a binary coin flip that has probability P, then the entropy of that event would look like this. Would be highest when probability P is half, and will be lowest when probability P is either 0 or 1. It will basically be certain in that case. We're going to talk about mutual information as well of two random variables x and y, which is just going to be the entropy of x minus expectation of entropy of x condition on y. Basically, this captures how much information on x we would get if we had observed y. We're going to get much more intuition into these two quantities. So the predictive entropy is going to be the entropy of the predictive distribution. We're just going to take those two equations that we had over here, we're just going to plug the predictive distribution into here, and we basically have a sum over the possible outputs, over the possible classes, of the probability for class yes diabetes times log probability, and no diabetes times log probability, and just sum these things together. As a note, mutual information, oh yeah, so in classification neural networks, we're going to use mutual information between model random variables W and model outputs Y star, conditioned with some input X star, which is going to be the predictive entropy, thing that we had over here, minus the entropy of the likelihood, where we take the expectation with respect to the posterior that we had before. And basically, we have a nice property that mutual information is always non-negative and always smaller or equal to the predictive entropy. Predictive entropy can be approximated fairly easily using Monte Carlo approximation by just doing the same MC stuff that we talked about before. Remember, this is just the integral of the over the posterior. We approximate the posterior of Q, so we just sample W from Q, and we average P of W. This will be high when the predictive is near uniform. So that basically means that we're going to get high uncertainty when either we have inherent ambiguity. For example, if you give me an input X that has training labels both 0 and 1, for that input X, we actually know, we can actually show that the elbow maximizer will be predict 50-50. In which case, we're going to get near uniform, in which case, we're going to get high entropy. It will also be high when we are predicting far away from the data, in which case, half of the draws will be 1, half of them will be 0. Averaging them will give us 50-50, and the entropy will be high. Mutual information can be approximated as, we're just going to look at the second term, because the first one is just what we had before. We have over here the likelihood, which we know what it looks like, so we just need to approximate this thing. We're going to sample W's from the posterior, which approximates this thing, and then just evaluate the entropy of the likelihood on each one of these W's. This would only be high when we are far away from the data. Basically, it has property that second term equals the first term, second term equals the first term, if all the function truths are the same for some input X. On the other hand, the second term will be naught, will go away when the function predictions are confident but also all over the place. I.e., this property, this uncertainty captures only epistemic uncertainty. Captures compared to predictive entropy, that basically which captures both epistemic and aleatoric uncertainty. So this is a pretty picture of what these things look like. We have some function draws over here, The predictive entropy will be high over here because we average these. We're going to get 0.5, therefore it's going to be high. Over here we have 0.5, it's going to be high. The mutual information is going to be that minus the entropy of each individual function. So entropy of that will be naught over here because it's near confident. Entropy of that will be naught over here because it's near confident. But averaging the entropy of each one of those is going to be high over here because all of them go through the 0.5, 0.5. Therefore, entropy, each one of these entropies will be high, and when we subtract them, you're going to get, this thing is going to go away, and we're going to get only high uncertainty when we are far away from the data. Predictive entropy will be also high when we have near the data, but we change classes, or like we're basically very ambiguous. I hope that makes sense, because we're going to talk about stochastic inference in deep neural networks now. Actually, I think this is simpler than what we talked about so far, because if you remember stuff from yesterday, it's going to be exactly the same. We're going to go back to regression, where we have the outputs, but it's the same if you do classification as well. We're going to talk about higher level stuff now. The elbow that we started from was the integral of Q times the log likelihood minus the KL between Q and the pi distribution. The log likelihood, for example, could be a square difference if we're doing regression, or the log softmax if close entropy, or log softmax if you're doing classification. Approximate posterior Q is going to be a normal distribution again. And we did Monte Carlo integration by just sampling some epsilon, reshaping some stuff, plugging that into the elbow, throwing away the integral sign, and we got this objective. I hope this looks familiar, because if you've done deep learning, everyone jumping. If you've done deep learning, then this should look very similar, very, very familiar to you. This last equation over here. Yeah. Mm-hmm. So I was wondering why can't we also do the prediction integrating out the variation line of the submatch? Well, so that is what, yeah, so that is actually what we did, and you can go over the equations a bit slower, but that is basically what the equation over here is. So we have P of y condition x and d. In the case of regression, that will basically be a Gaussian likelihood times a Gaussian posterior, in the case from yesterday, which is going to give us another Gaussian predictive distribution. Over here, we have a Gaussian posterior, but we have a categorical likelihood. So when we integrate over the Gaussian posterior, we're going to get something that looks like this. We're going to get a distribution over probability vectors, basically. Well, we're going to get probability vector, basically. So, which is probability of taking some value C is going to be the average of the probability for C under each draw from the Gaussian distribution. So it's actually it's a probability basis equal to 0, 1. But could I also compute predictive variance? So predictive variance is challenging to define in the simplex, because predictive variance would imply that, for example, so you can define the variance for a categorical distribution, which I don't think is too interesting. You can take the, just like the normal definition of variance for these samples, which is like, pretend that these are samples from some Gaussian distribution, and compute like mu minus whatever it is, like the normal definition for variance for continuous variables. Which is not going to give you too sensible output, because that will basically tell you that, for example, a 95% confidence interval could be outside of the simplex, could be outside of the unity interval. Yeah, for if you have like 0.9 plus minus 0.2, what does that mean? So that's why we actually end up using these different quantities, predictive entropy, mutual information, to estimate how certain we are in classification tasks. the thing that we're just talking about, which is just looking at the sample variance of a bunch of probability vectors, can actually be seen as an approximation to the mutual information, which is the second thing over here, second term over here. How much time do we have? No, I'm just trying to understand, and I'm trying to plan. Okay. So, okay. Yeah, okay. So this should look familiar. Which also would imply that it shouldn't be too difficult to extend what we did until now, which was only for the last W, last layer, to all other weights as well. And basically, until now, doing inference on preceding layers was too challenging because of intractability or non-conjugacy. But with these new tools, we can actually do stuff very, very easily, and I actually think even easier than yesterday. We're going to define all W's, W being the model. All of them we're going to collect under one unknown variable omega to make stuff easier. X is going to be some n by q input, W1 some q by k matrix, W2 some k by t matrix. Phi is going to be some element-wise nonlinearity. Omega is going to be the collection of all of these unknown variables. F omega is just going to be phi of x transpose W, 1 times W2 plus B2. So this is basically a neural network. Could also be thousands of layers deep. I'm going to keep it only 2 layers so it's easier to talk about what we have over here. This model, when W is a stochastic random variable, is called a Bayesian neural network. This model, like this sort of tools, these sort of models actually have very long history, starting from, as far as I could find, at least 87 by Hopfield. Jan LeCun worked on this in 1991. David Mackay worked on this in 92. Jeff Hinton worked on them in 93. Radford Neal in 95. David Barber and Chris Bishop in 98. The model is very simple. The model is exactly the same as before. We just swap W1, W2, F omega instead of W and FW. That's all. We're not going to talk about that more. Approximate inference is also exactly the same. So all the time that we spend building all these things for simple classification tasks, one-layer models, it's all exactly the same. Log likelihood is the same. The approximating posterior, which was a Gaussian, now is just 2 Gaussians with means M1, sigma 1, and standard deviation, well, means M1, M2, and standard deviation sigma 1, sigma 2. Kullback-Leibler to the prior, because of independence, just going to be the sum of the Kullback-Leiblers. So the elbow is going to be just sample W hat by sampling epsilon hat multiplied by sigma, add to M. Sample W2 hat by sampling another epsilon multiplied by sigma squared 2 by sigma 2, add to M. And just plug these into the elbow. You're going to swap F theta epsilon that was before single layer with a 2-layer model. And just all of these are going to go into the elbow and we're done. Now we have approximate inference on deep neural networks, deep Bayesian neural networks. So people asking about that yesterday, that's all. So this actually was proposed from the compression perspective as minimum description length. Literature was talking about, well, not really talking about Bayesian neural networks at all, was not talking about uncertainty at all. This was a paper, for example, by Graves from 2011. In Bayesian modeling, this technique is known as mean field variational inference, MFVI. This is also called Bayes by backprop, following a paper by Charles Blundell from 2015. Yeah? think the simplest answer is that it depends on the application. In certain applications, if you do this, if you use this assumption, you don't see a big difference in terms of actual performance, what uncertainty looks like, or different things that you would use uncertainty for. In other applications, you would see a big difference. At the end of the day, it depends on the posterior correlations between the variables and how justified this assumption is. I'm actually going to talk about some other issues that we have with this method, which is scalability. So when we use very large models, when we use deep learning, we try to use as large models as we can fit on the GPU, usually tens to hundreds of millions of parameters. If you have more memory in your GPU, you're just going to use a larger model and try to get better results. When you use a Gaussian approximating distribution, we need to use at least 2 parameters for each neural network weight. This M and sigma that we have over here. Doubling the number of parameters or halving the number of effective parameters, like reducing model size by 2. So can we scale these things up to even larger models, like the ones that we use in computer vision, the ones that we use in autonomous cars, going back to autonomous cars? So let's look at inference in very, very large deep models. For that, we're going to talk about stochastic regularization techniques. And lots of techniques inject noise into very large models to help with regularization. Dropout is one of them, suggested back in 2011, stated thousands of times, still used in most deep learning models. I'm going to talk about dropout, but there's lots of other very basically work the same way. At training time, dropout basically randomly sets network units to 0 with some probability p. So this is called the stochastic forward pass. At test time, normal dropout multiplies each unit by 1 over 1p, 1 over 1 minus p, and does not do dropout. This is called the deterministic forward pass. Noise is added to the units, the feature space, and is implemented in every deep learning package you can imagine, including TensorFlow, PyTorch, TensorRT for better devices, for the weird Intel stuff, and so on. Over here, I have exactly what we just said, just in mathematics. I think I'm going to skip that because, yeah, okay, let's go over that very quickly. X, again, is q by 1 vector. What we just said is just x hat is just going to be x transposed epsilon hat, where epsilon hat is just going to be a matrix, q by qu matrix, that has zeros off diagonal and Bernoulli's on the diagonal. So we basically multiply each element in X by Bernoulli, that's the same as multiplying that by a q by q matrix. Plug that x hat into phi, so we have x hat times w or m over here, plus b. And then we're going to do the same thing, I'm going to call that h, I'm going to do the same thing for h. We're going to multiply that again by k matrix now, that has diagonal of Bernoulli's. I'm going to multiply that by m, I'm going to get some y hat, and plug that into our objective, which is just going to be L2 Euclidean distance plus L2 regularization. Everyone is happy with that? This is just normal deep learning. Yeah? We don't have anything fancy over here. Now we can actually take that normal deep learning and transform that noise from parameter space, well, from feature space to parameter, to weight space, by just taking that x epsilon hat m and just moving these parentheses from here to here. And we're done. Just going to write w hat to be m times epsilon, or epsilon times m. W2 is just epsilon 2 times m2. So we can basically write y hat, stochastic forward pass, equals phi of x times w1 hat, which is stochastic matrix now, plus b times w2 hat, which is another stochastic matrix. Or we're just going to write it as f of omega hat, with some w hat 1 and 2, some realizations from those stochastic matrices. So at training time, dropout sample weight matrices, which looks very, very familiar. Basically looks exactly like we just did so far. And let's see if we can make this connection a bit more formal. We're going to develop approximate inference in Bayesian neural networks with a new type of approximating distribution. The model is again exactly the same. Likelihood is exactly the same. Approximating distribution of W1 just going to be m times epsilon, where epsilon diagonal is going to be Bernoulli some probability p. Same for W2. Theta is a collection of m1 p1, m2 p2. The Kullback-Leibler between this Q distribution and the pi distribution we had before, you can show that it's going to be very, it basically approximated very closely with this quantity over here, which I'm not going to go over. The elbow, in that case, is just going to be the log likelihood with this f of theta and epsilon hat plus this KL to the pi distribution. And we can rewrite that slightly differently. We're going to multiply everything by a constant minus 2 sigma squared over n. And we're going to get the same objective that we had for dropout, where yn hat is just f of theta and epsilon hat. And we define lambda 1 or the L2 penalty just be sigma squared times 1 minus p1 over amount of observation noise squared times n, number of data points. That's all. This is the normal dropout objective, i.e. any standard neural network in which you use dropout. You can view that as a Bayesian neural network, get uncertainty from that. Do note that we need to tune p as a variational parameter over here. We can't usually differentiate with respect to p because we have a Bernoulli which is not differentiable. We can't use the reparametrization trick. You can do grid search though over p. Instead of to maximize the validation accuracy, you can do that to maximize the elbow or the validation log likelihood, log predictive. You can also use continuous relaxations like concrete dropout to optimize for p itself. This is an example that we started from yesterday. I hope everyone is waking up. I know it's very late, it's 5 p.m. and everyone is very tired from a long day, but we're basically almost done with all the mathematics. We're just going to look at some fun applications soon. This is exactly the same code that we had yesterday. We have some deep network, we have some dense layers, we have some dropout layers. We compile that. Now we also have regularization term added, which I skipped yesterday because now you actually understand what it does, where it comes from, why that's important. So we add L2 penalty, but that's exactly the same equation that we had before. Now we can do uncertainty estimation in these BNNs almost trivially. Predictive mean, remember, was this equation before that you asked about. Averaging multiple stochastic forward passes. Predictive variance is just taking sigma squared plus, I'm not going to read that. I'm going to skip these derivations. But basically, if you want to implement stuff, then it's as simple as just do a bunch of forward passes, a bunch of stochastic forward passes through your model, 100 in this case. You call numpy.mean over the first dimension, numpy.variance over this first dimension, and you're done. How do you visualize a Bayesian neural network? It's very simple. We're going to sample a set of weights, omega, from the posterior over omega, over the parameters, which is the same as sampling a function, f omega. We're going to evaluate that function over the interval minus 10 to 10, which in practical terms means that we're going to sample an omega, and for that fixed omega, for each xi in minus 10, minus 9.95, minus 9.99, we're going to evaluate yi equals f omega of that xi. We're just going to plot all of these together, and we're done. Do note that if using just naive implementation of dropout, then you often actually end up using different masks for every stochastic forward pass. So you're going to get results that look like that. We can actually look at visualization on this link or on the original page for all the examples, all the resources online. Question? No? Okay. Okay, we're done. Let's just look at some fun applications in the last 10 minutes. Real-world applications of model uncertainty. How can we do deep learning with small data? How can you get big models working with small data? So that's actually a very, very big issue that we have in the field, that usually you need huge amount of data if you want to do deep learning. And getting huge amount of data is expensive or infeasible. If you want to do medical applications, it's difficult to find lots of patients that have certain type of rare disease. If you want to do your own startup doing some deep learning stuff, usually it's difficult to get lots of funding for lots of people to sit down and label your images and your data. Or if you look at machine learning in other like scientific applications, we often use machine learning to aid experts working in laborious fields to automate small parts of the pipeline, of the work pipeline. For example, in this case, it's melanoma cancer diagnosis based on lesion images, and we want to help them get better results faster with the small data that they have. Yeah, so this if you actually look at like the state-of-the-art results that we have in the field, like ImageNet, requires hundreds of gigabytes of labeled data. You want to have very large models to get good results. You need very large amounts of data to get large models working well. Complexity of the input data increases with the complexity of the model increases with the complexity of the input data, and we can't afford to label these huge amounts of data. So instead, we can use active learning. Active learning is very simple. We have an agent that chooses unlabeled data, but specifically chooses the most informative unlabeled data. So it's going to ask an external oracle, for example, a human annotator, for a label only for the points that it thinks that will actually help it. Only for the points that it thinks that will help it improve its performance. For that, we need to define some acquisition function, which basically takes points, unlabeled points, and ranks them based on how informative they would be for us if we had a label. So, for example, we could use epistemic uncertainty. This is actually the training circle. So we basically continue doing that back and forth. We train a model on some labeled train set. Evaluate that, evaluate some acquisition function on a large unlabeled pool set. The expert only labels the pool points that have the highest acquisition value, add these points back to the training set, and then repeat. It's very simple. If you want to use uncertainty, then let's look at a concrete example. MNIST, active learning, that's actually also the stuff you're going to play with in the tutorial. We're going to compile some model that does some classification, categorical cross entropy. We're going to predict 20 times to get some Monte Carlo samples. We need some uncertainty for classification. It's as simple. We had lots of mathematics, which basically ends up as these two lines of code. So predictive entropy is going to be take the Monte Carlo samples, take the mean to get the expected P, and just take the negative sum of expected P times log P. That's all. Mutual information is going to be these 3 lines of code. It's going to be the MC entropy, which is the entropy of each sample. We're going to average these over the different samples to get the expected entropy. And we're going to take the difference, predictive entropy minus expected entropy equals mutual information. That is 3 lines of code and 2 lines of code. And if you can go back over the slides later on to explain to yourselves why we have basically these 2 lines of code, 3 lines of code, and 5 lines of code that we had over here. Anyway, so doing this cycle where we ask mutual information, which is called BOLD over here, based on the paper that suggested using mutual information. It's called Bayesian active learning by disagreement. And basically we ask the model, tell me which points you want me to label out of MNIST, and then you sit down and label these, or just query an oracle for these labels. And then we can actually show that we can get very nice results using only 1,000 MNIST examples. We can get more than 98% accuracy. More interesting, if you go back to the example of melanoma classification, skin cancer classification, we can actually do melanoma diagnostics with only 300 images. And much more interesting than 300 images is the number of the different types of images that the model asks for labels. So over here, you have the one that uses mutual information, and we have a baseline. We just randomly select, I want that point and that point, that point, without even looking at them. And you can see if we look at the number of positive classes, or like yes melanoma and cancer as examples, then the one that looks at the mutual information basically very quickly exhausts all the positives in the data set and then says, okay, give me that label for that boring negative example if I must take a label. Can look at, should I do that? Okay, let's do that quickly. So you can look at another example, which is the one that we started from again yesterday, diabetes retinopathy diagnostics, where the goal, in this case, is to detect diabetes and be able to tell when the model is guessing at random. So we can use that model, for example, for pre-screening, where we only send patients that have high uncertainty to an expert, and other patients where the model says, oh, that's definitely not diabetes, we just say, okay, no diabetes. So how do we actually know if we can trust our model's uncertainty? So this is actually a very important question. There are a bunch of different metrics that we can evaluate in order to see whether uncertainty even makes sense or not. So let's define a binary event, in this case, is diabetes, yes, no. So basically, I'm going to group this test set inputs by prediction, yes or no, versus the labels, yes or no. For each one of these, we're going to get a corresponding true positive, false positive, true negative, false negative. From these, we can get true positive rate, false positive rate. I'm going to skip that. In general, we want the true positive rate to be high. We want the false positive rate to be low. Usually, we're given the requirements of what's the most the model is allowed to do before we are allowed to deploy a model in the real world. For example, true positive rate must be 0.7, false positive rate must be at most 0.1. So now the model predicts probability P of y, condition x and d. How do we actually get a recommendation? Do you have diabetes or not? Naive thing to do is just to take the argmax, i.e. if it's larger than 0.5, say yes, you definitely have diabetes. Sounds very silly, because what if the model predicts 0.51? You don't want to say yes, you definitely have diabetes. So what we can do is define a threshold t. If the predictive probability is higher than t, then say yes, otherwise say no. So for t equals 0, we're going to say yes to all patients. For t equals 1, we're going to say no to all patients. For each threshold t, we're going to get some false positive rate, true positive rate pair. We're going to scatter all of these points, all of these different t's. That's basically what we call an ROC, receiver operator plot, where we want to have a high area under that plot. It basically shows us the trade-off between true positive and false positive. Each point corresponds to a choice of t. We want to find a model that gives us a large area under the curve. How can we improve that area under the curve? So one thing that we could do is identify the patients where we are guessing at random. Select the 10% patients on which we are most uncertain and just refuse to say whether they have diabetes or not. Send them to an expert. If the uncertainty that your model gives you actually correlates to mistakes that you had on patients, ROC, the AUC and the ROC should go up. So, blah, blah, blah. What uncertainty should you use? I'm going to skip stuff. I'm going to use expected entropy. You can go over that later. Picture. So over here, if we have no referral whatsoever, we're going to get this nice blue line, which shows us the sensitivity, one-man specificity, or like false positive, true positive rate for our model, for an actual model that was published in a Nature paper. And as we use uncertainty, using the tools that we just saw before, to send patients to an expert, if we send If we send only 10% patients to an expert, we get a slight improvement. 20% we get a slight improvement. 30% we get an even bigger improvement. You can basically see that we get better and better as we reject more and more examples. We refuse to classify more and more examples. If your uncertainty was stupid, then this could actually very much go down because you end up sending patients in which you were classifying correctly. You end up keeping only the incorrect patients. Another nice measure of performance is just looking at the accuracy as a function of number of retained, percentage of retained data. As we send more and more patients to an expert, 100% retained data, original accuracy over here, 10% retained data, accuracy after removing 90% of the patients, high uncertainty over here. And again, if your uncertainty is very stupid, instead of basically going down, it will start doing like some weird stuff. So it's a very good way to diagnose whether your uncertainty makes sense or not. Question, yeah. It's not, so relabeling was the active learning case over here. It's not necessarily relabeling. You just say, I'm not going to trust. We don't have a label. Yeah, we don't have a label for this because that's a new patient I never saw before. When I deploy my system in the real world, I don't have a label. So I just have the prediction for my system and the confidence in the prediction based on the uncertainty.
Now assume you send those patients to, or those data points to an expert label.
Yeah.
Integrate them back.
Then you can bring them back and reduce the uncertainty.
Yeah. My question is, can you, from the predictive entropy which you measure for those data points you are having relabeled, infer how much better your model is going to be after you know the labels? To justify, say, that it's worth the effort?
I think like worth the effort in the sense that you have to diagnose these patients anyway because they come to you saying, can you please diagnose me? Worth the effort of adding that data back into the model. You mean worth the effort of adding the data back into the model?
No, the effort. So I want to send these certain amount of data points to an expert, and that costs me $2,000 per data point. These cases where you don't get it for free. And then I want to justify that it's worth it.
Well, it's worth it in the sense that if you didn't use the system, then you would send all of the patients to the expert. So if you can reduce expert load even by 10%, that's reducing expert costs by 10%. Or making that...
I agree with you. My question was, can you infer how much it will get better? The answer can be no.
How much the system would be better?
Can you quantitatively infer how much you can hope to get better?
I would say in broad terms, it will still be fairly dependent on the type of uncertainty for why you send the patient to the expert. So it could be one of two cases because again, we're talking about the predictive entropy over here. It could be that the patient was very far away from any patients that you've seen before, in which case adding that patient to the training set could reduce uncertainty for future patients as well. And then a future patient, you would say, I don't need to send that patient to the expert. I've already seen something very similar. But it could also be that it's a patient that comes from an area of the data set that you have huge amount of noise. So we didn't talk about heteroscedastic versus homoscedastic noise, but often you can have some parts of the input space that have very noisy data. For example, you might have some instruments in some hospitals that are very noisy. So you know that some patients coming from certain areas would actually have a very large amount of noise in the actual data. In which case, even if you get a label for that, you will still have the inherent noise in the instrument itself every time you send a new patient from that hospital. I'm going to give the same answer. It basically depends on the scenario and the exact application that you're looking at. I'm going to skip the autonomous driving example because we don't have time. So I'm just going to, we had some fun stuff talking about Altro's convolutions over here and talking about ResNets and talking about exception models. And I'm just going to summarize very quickly some other applications if you want to read more about how we actually use these things in the real world. So this is a Nature Scientific Reports paper on using uncertainty tools that we talked about over here for disease detection. So this is where I took the plot for the diabetes retinopathy diagnostics. People use these tools in robotics, for example, to do uncertainty-aware collision avoidance. We use these tools in urban remote sensing, so for example, in Earth observation data. We use these tools in astrophysics. People have been using these for strong gravitational lensing example. Example I talked about at the beginning, that is an actual real world example. It's the one from yesterday, that people have been using these tools to get uncertainty estimates for these applications. Uber is using these tools to get time series prediction, and they actually had a nice blog post summarizing some of the stuff we talked about over here in the context of how they use it for their applications. So what you should be able to do now, after this very long lecture at a very late time of the day, you should be able to use uncertainty, at least in regression correctly. You should be able to perform predictions in simple probabilistic models efficiently, and use Bayesian modeling in complex machine learning models. For example, classification. I would suggest everyone to go back over the slides for that again. Should be able to use uncertainty, both epistemic and adiatoric, in real-world models, and extend VI correctly to new applications, to new complex models. Try actually to do that at home, replacing the Gaussian likelihood with the Laplace likelihood. Or try to do multiple outputs, categorical and a continuous variable output. You can actually even try to derive variational autoencoders if you want from these tools that we talked about here today. You have all the foundations that you need to derive variational autoencoders, talking about graphical models, or generative models at least, generative stories, talking about variational inference, reparametrisation trick, and so on. You can do deep learning with small amounts of data. You can try that at home, where you can actually get a big deep model working with a small amount of data. You can evaluate whether your uncertainty makes sense or not. And you can somewhat understand how huge deep vision models work, which we skipped, so you can't do that last point. Yeah, that's all. Thank you so much.